So yeah, the plan for this is just to kind of set out what the landscape of this debate is for people who might not be so familiar with it. So, ooh, I can't make it go to the next slide. Okay, there we go. So this topic is kind of at the intersection of two different issues. The first is the nature of the quantum state, and the second is the foundations of statistical mechanics. So the first half of this talk, I'm going to talk about the nature of the quantum state, and then I'll talk about the foundations of StatMech. Okay, so the kind of dominant view in about the nature of the quantum state is wave function realism. And according to wave function realism, the fundamental ontology of quantum mechanics is the wave function defined on a high dimensional space, which is the 3n configuration space. And consequently, the wave function realist claims that configuration space is fundamental and ordinary space is either illusory in the view of David Albert or emergent in the view of Alyssa Ney. And one feature of this view is that the quantum state on this higher dimensional space is separable. So that's a kind of a very quick and brief sketch of the wave function realist position. And so that's one answer to the question, what is the nature of the quantum state? What does it tell you about physical reality? But some deny that the quantum state is telling us anything. One camp of those who deny that the quantum state is telling us about the world are known as kind of psi-epistemicists, such as Harrigan and Speckens. And they claim that quantum states encode observers' knowledge of reality. So there's kind of different grades of realism. The first kind of weakest grade is the view in opposition to psi-epistemicism, which is kind of psi-ontic. So this is the terminology often used in foundations of physics rather than so much in philosophy of science. And according to either the rho-ontic or the psi-ontic view, the quantum state is telling you about reality rather than just encoding observers' knowledge of reality. And then on the other end of the spectrum, we have like realism with capital R, where we have to pick one representation as fundamental, i.e. the representation that carves nature at its joints. And so unlike the kind of rho-ontic or psi-ontic view, you have to pick either the wave function or the density matrix to be a realist about. So, you know, the psi-ontic person could say, well, the wave function tells me about reality, as does the density matrix. In this stronger realism, you have to pick one or the other. And in the middle, you could have something that you could call realism light, according to which we don't have to pick one representation as kind of the representation, since some representations you might think of as being theoretically equivalent. But nonetheless, one formulation might be more kind of conspicuous than another. So for instance, Wallace and Timpson in their version of rho realism are motivated by having an account of the nature of the quantum state that kind of emphasizes the role that space-time plays and makes sense of the failure of narratability. Or you might think that one representation might be more helpful for theory, future theory development. Okay, so how should we understand rho? So density matrices are usually brought into a course in quantum mechanics after you've already learned about the wave function, either as probability distributions over wave functions, or as the state that results from tracing over the environment that a system is entangled with. So this, I think you can see my little pointer thing. So if this is the kind of joint state of Alice and Bob, this is the state that represents Alice's state if by tracing over Bob's state. So if Alice and Bob are entangled, you can only represent Alice's state using a density matrix. You can't give a wave function representation. So in that sense, the density matrix representation is more general than the wave function representation. And whilst these are kind of conceptually different objects, there's no measurement that you could make on Alice's system that can tell these types of states apart. And that's why I'm going to give them the same symbol, rho, to represent them. And so whilst we learn about rho after we've already learned about other representations of the quantum state, for the rho realist, nonetheless, it's not that we should think of rho as being derivative on psi, but rather rho is primary. So the key idea is that rho is fundamental and shouldn't be thought of somehow an incomplete description. Okay. And so there's this kind of different accounts or versions of rho realism, which we'll hear about some of them today. So on Eddie's view, the density matrix, which you should be a realist about, is the fundamental density matrix, which I think Roddy will also talk about in the case of Birmingham mechanics. and it applies to the whole universe. And consequently, part of Eddie's view is that the universe is in a mixed state. On Owen's view, the weights are not to be understood as mixtures, I believe. I think Owen will also tell you more about this later. And since Owen calls it rho-ontic, perhaps he's committed to a slightly weaker form of realism. Okay, and on Wallace and Timpson's view, they call this space-time state realism. You assign density matrices to regions of space-time. So for Wallace and Timpson, they're not focused on the universal density matrix. Instead, they're motivated by the fact that most systems will rapidly become entangled with other systems, and so only can be described by rho and not psi. But you might think that non-separability, i.e. the fact that the state of the joint system is not completely specified by the states of the subsystems for entangled systems, pushes us to consider larger and larger systems if we want to capture all of the information about a given system. But this doesn't require that the universe is in a mixed state rather than a pure state. So it could be that you're kind of pushed to consider bigger and bigger systems in this kind of slightly holist manner. But nonetheless, you can still think as the kind of state of the universe as being in a pure state. Whereas on Eddie's view, he requires that the universe is in a mixed state. And I think this has a kind of certain dialectical force against the wave function realist. So you can imagine the wave function realist saying, yes, well, the density matrix is kind of a useful, kind of an unfortunate thing that we have to use when a system is entangled with other subsystems. But ultimately, the universe is in a pure state represented by the wave function. And so rho only gives us a kind of incomplete description, so it isn't fundamental. But of course, if the universe is in a mixed state, that blocks this move. So if the universe is in a mixed state, that's kind of an advantage for the rho realist, but it doesn't cut the other way, in that if the universe is in a pure state, that's not really an advantage for the wave function realist, since the density matrix can also represent a pure state. And one hunch which I'd be interested to see whether other people agree with is perhaps we might think that which interpretation of quantum mechanics you prefer might come into how much you emphasize the importance of the state of the universe. So the universal wave function is in some sense primary over subsystems for Bohmians, whereas local subsystems that decohere in the branches of the multiverse are more central for Everett. So maybe there's a matter of emphasis depending on which interpretation you've got in the background. Okay. And these different versions of rho realism, I think, have slightly different motivations. So Eddie is motivated to present a kind of harmonious package of views which are going to pin down the past hypothesis. I'll come on to explain what this is shortly, and reduces the statistical mechanical probabilities to quantum mechanical probabilities, and there's other kind of features of the package as well, which I won't discuss now. In a talk that Owen gave a few years ago, he was motivated by understanding the asymmetry in thermodynamics. And Wallace and Timpson are kind of like the odd ones out in that they're not motivated by statistical mechanics, but are instead motivated by understanding non-separability. And my motivation, which I think aligns with, from what I've seen from Owen's talk, Owen's motivation, I want to use rho realism to kind of rehabilitate the Gibbs entropy from its bad reputation. So some people don't like the Gibbs entropy because it's defined in the classical case with respect to probability distributions, and people worry that, well, the classical system is in one particular microstate. There's this probability distribution over possible microstates that the system's not in. So how are we meant to connect to this quantity, the Gibbs entropy, to the particular individual system that I'm interested in? Okay, so now onto the foundations of statistical mechanics, since this motivates some of the views for rho realism. So there's kind of two entwined issues in statistical mechanics. The first is, how should we understand the time asymmetry? To be very loose, how entropy increases, but maybe there's more careful ways to describe the time asymmetry, given the underlying time symmetry. And how should we understand statistical mechanical probabilities? Where do they come from? So probabilities are central to statistical mechanics, of course. But why do we use these probabilities? Is it because we just don't know the exact microstates? We can't measure the exact position and momentum, or do calculations with 10 to the 23 particles? If so, it seems like the probabilities in StatMech come from our ignorance. And you might worry that this is kind of bad news in that it makes stat-mech incompatible with scientific realism. It brings in this kind of element of anthropocentrism that you might think is not conducive to realism. And perhaps more pressingly, you might wonder, well, why would incorporating ignorance help us gain knowledge about the world in the way that statistical mechanics does? So other philosophers of physics share this worry. So Callender and Doherty say, well, the efficiency of the steam engine doesn't care about our beliefs. And David Albert, with his typical rhetorical flourish, says, can anybody seriously think that our merely being ignorant of the exact exact micro conditions of thermodynamic systems plays some part in bringing it about, in making it the case that, say, milk dissolves in coffee? So the theme of the second half of this talk is going to be to say that the statistical mechanical probabilities don't need to be understood in terms of ignorance, but instead come from quantum mechanics. And in particular, row realism can help us understand the use of probability in stat-mech. And I'm going to look at two different strategies, one which is a kind of more global strategy, and one which is, for want of a better word, more local. Okay, so how should we explain? So I said before that the asymmetry, the question about asymmetry was connected to the question about probability. So how should we explain the asymmetry of statistical mechanics given the symmetry of the underlying microdynamics? There's kind of two different paths for thinking about this. There's the Boltzmannian path, which I'm going to discuss in a second, but one path which I won't really talk about now is the Gibbsian approach, where you construct the irreversible equations from the underlying dynamics using something like the Morey-Swansig framework. But even in that framework, it's similar to the Boltzmannian account and the examples I'm going to consider here, in that they all involve some kind of initial condition. So to give you an analogy, in the case so there was this debate between Einstein and Ritz about where the asymmetry of electromagnetic radiation, where we were always seeing waves going outwards but never converging inwards. And Einstein's response was, well, it's a bit like the kind of ripples we see on a puddle. The reason why we always see ripples going outwards rather than converging inwards isn't because there's something intrinsic to the ripples in a pond, but rather because we're always throwing stones into a pond. So in the same way, the kind of asymmetry in statistical mechanics is going to come from initial conditions. So to answer the question, why does entropy increase? There's a framework discussed by David Albert and Barry Lower called the Mentaculus, which is meant to give you a kind of probability map of the world. And this follows the kind of Boltzmannian combinatoric answer to the question, why does entropy increase? The idea is that there are many, many more microstates that correspond to the equilibrium macrostate, so this larger state here. And so it's inevitable that a system not in equilibrium will wander into that macrostate. There's various caveats to be made, but I won't go into that now. But this diagram is kind of a bit misleading in some way, because the idea is that this equilibrium macrostate should be like overwhelmingly larger than all of the others. In a way, it's a bit of a misleading diagram. This is a diagram from Penrose. But this argument faces what's known as like the kind of parity of reasoning objection. So just as we expect entropy to increase towards the future, because it's just likely that a system is going to wander into the equilibrium macrostate, we can also kind of turn and face the other way, and it looks like the same argument would lead us to predict that entropy was higher in the past. So to avoid these kind of disastrous retrodictions, clearly we thought that entropy was lower than it is now in the past. The idea is to move the initial state, the initial condition all the way back to the beginning of the universe. And this is what Albert calls the past hypothesis. The initial state of the universe was in a low entropy macrostate. But this framework also needs another condition known as the statistical postulate. The probability distribution over this low entropy macrostate is the uniform distribution. There are various worries about the past hypothesis, but I'm not going to get into them today. Okay, so we're going to hear more about this from Eddie, but this is a quantum version of the Mentaculus. Eddie calls it the Wentaculus, since sometimes the density matrix, instead of being labeled by rho, as I've done, is sometimes labeled by W. So we'll hear about this more later, but just briefly, the idea is that by combining row realism and a different past hypothesis, you can eliminate statistical mechanical probabilities. So by having, instead of having Albert's past hypothesis, you instead have what Eddie calls the initial projection hypothesis, which is the uniform projection over the past hypothesis subspace in Hilbert space. And because this is already a probabilistic state, you don't need to add in the statistical postulates that Albert has in this quantum version of the Mentaculus. So in this way, you haven't had to add in any probabilities in addition to the ones that you've already got from quantum mechanics. I have a couple of concerns about the global root, which I'd be interested to hear what people think about later. But I guess my main question is, why should we think that theories such as statistical mechanics and thermodynamics are theories that have an unrestricted domain and apply to the whole universe? With the exception perhaps of a fundamental theory of quantum gravity, we usually think of physical theories as having a limited domain of applicability, i.e. only applying in a particular regime. For instance, Newtonian mechanics applies when mass is not too big or too small, and the mass is not moving too fast. There's Navier-Stokes equations apply when fluid can be modeled as continuous medium, etc., etc. Yeah, I guess I wonder whether statistical mechanics and thermodynamics should apply in this unrestricted way. Maybe they should, but that's and I think perhaps the reply that those advocating this global route, either the Boltzmannian version that I've gone through or the Gibbsian version that David Wallace advocates, maybe the kind of charitable reply is these kind of global strategies are kind of schemas for recovering macrophysics more generally from the underlying microphysics, and will be filled in by more detailed stories in particular patches. So in the same way that I've said, physical theories often have like limited domains in different patches, this is kind of like more like an overlying strategy, which will apply in more detail, with more kind of details filled in for other cases. And it might also be that perhaps this global route has kind of different explanatory aims than other routes. Okay, so now on to the second route, which I call the local route or the subsystem route. And the idea for this route is likewise to show that statistical mechanical probabilities really came from quantum mechanics rather than being an additional ingredient. So the key idea is that for a subsystem in thermal equilibrium, the canonically distributed state is its individual state, rather than a probability distribution over individual states, only one of which the system's truly in, i.e. it's in an energy eigenstate, we just don't know which one of the energy eigenstates the system is in. And I think this, going back to Schrödinger, also this paper by Goldstein et al. And Wallace have all argued that a system in thermal equilibrium shouldn't be thought of as being in an energy eigenstate. So we shouldn't think of the system as really being in an energy eigenstate, we just don't know which one. Okay, so how you get to this kind of idea is that, so if the joint system, so the system in the environment, which may be something like a heat bath, is in the maximally mixed state, i.e. the microcanonical ensemble, then the system, i.e. that part of the joint system, which is the system, will be in the canonical state. But you might worry that this maximally mixed state is a proper, i.e. statistical mixture, and so involves ignorance or kind of epistemic probabilities. You might think that really we brought in the maximally mixed state for the joint system because we didn't know which state it was in. So I think the kind of first reply to that, because that would of course bring in ignorance again, which is exactly what we were trying to get rid of from our account of statistical mechanical probabilities. The first reply might be, well, you should be a density matrix realist. You shouldn't think of the joint system state as being a statistical mixture when it's really in one pure state, but rather you should think of the density matrix as describing the fundamental state of the system. It seems like there's two ways you could think about that. You could either think, I take the density matrix as fundamental, and that's ask no further questions. Maybe that's a little, well, that's one way to go. And then another way to go might be to think, well, really, the joint system is going to be a large system. It's going to get entangled with other systems, and so really we should think of that as being in a mixed state. But even if we think that the joint system, so the system and the environment, i.e. or the system and the bath, even if we think they're in a pure state, then you can still show that the system is in the canonical state. Roughly, the idea is that the environment is much larger and the system will be entangled with the environment. So there's this nice result by Goldstein, Leibowitz, Tomolka, and Zangi, which they call canonical typicality. And there's another paper by Popescu et al. Who showed the same result in more generality. And the idea is that if this environment is sufficiently large, then for pretty much any pure state that the composite system, what I called earlier the joint system, the system and the environment, is in, then the system will be in a state very, very close to the canonical state. And so it seems like the system, which I should have given an example, you could think of that as being your gas in a box, behaves as if the composite system were in the maximally mixed state. So at this point, you can either think of the maximally mixed state as representing the genuine state of the joint system, or you can think, actually, that's in a pure state. But even if you think that, your system of interest, your box in a gas, not a box in a gas, your gas in a box, other way around, will behave as if the system was in the maximally mixed state. Okay. So this result answers a kind of how possibly question, like how can we get statistical mechanical probabilities like the canonical distribution without adding in another source of probability? And it further bolsters the kind of reinterpretation strategy that the density operator of the system should be interpreted as the individual state of the system, i.e. an improper mixture, rather than a probability distribution over the possible states of the system, i.e. a proper mixture. But note that by relying on this kind of analysis, we've relied on the fact that the gas in the box of the system is entangled with the environment or the bath. I've relied on it being a subsystem. And so we can't apply this analysis, to saying that the universe is in the canonical state. But one of the things that I was wondering, maybe we'll get covered in this workshop today, is do we need to talk about the thermal states of the entire universe? I guess this comes back to the question of whether we should think of the domain of stat mech and thermodynamics as being kind of unrestricted. So one potential objection to this route is that, well, even if you've eliminated any distinctively statistical probabilities in quantum stat mech, what about classical stat mech? Since classical stat mech is an empirically successful enterprise and involves adding probabilities to classical mechanics, aren't there still some statistical mechanical probabilities? So the answer to this, given by Valentine and Wallace, is that we should think of the classical mechanical statistical the classical stat mech probabilities as the classical limit of individual quantum states, without a need for distinctively stat mech conception of probability. So Wallace argues for this by showing how, if you take the Wigner function on phase space, there's an approximate isomorphism between the dynamics of the quantum states and that of the classical probability distribution. He also goes a bit further to say, well, we can't really think of, even when we're not in the kind of quantum regime of cold or dense gases, even when we're in kind of classic kind of ideal gas territory, the wave packets of the gas molecule after a collision will be about 30 times the size of the diameter of the molecule. So it's not really very tenable to think of it as like behaving like a point particle bumping into other gas particles. Okay, so this has the happy consequence for me that if the canonically distributed state is the state of the individual system, then the ensemble objection to the Gibbs entropy doesn't really get off the ground. And so we can think that there's nothing subjective about the probabilities involved in the Gibbs or the Gibbs von Neumann entropy. But that's not to say there aren't some concerns about this strategy. So one concern you might have is that it's incomplete. So the results that I briefly mentioned are purely kinematical. And so there remains the question of the dynamical approach to equilibrium. The Mori-Svanzig framework, the more Gibbsian global strategy that I mentioned before, popularized by Wallace, is one approach to studying the approach to equilibrium, but it uses coarse-graining. Coarse-graining is not connected to ignorance. elsewhere, I've argued that we should think of it as an abstraction that allows us to uncover emergent, autonomous, irreversible dynamics, but it adds a certain complication, which is that coarse-graining leaves out some information. And so the coarse-grained state is not the same as the kind of complete state. And you might worry that this allows statistical mechanical probabilities to sort of get a foot in the door. It seemed like we had given an argument to say all stat mech probabilities were really quantum probabilities, but maybe this is saying that then the two things are, there's kind of a way for them to wiggle their way back. And whilst the coarse-grained state will often be a different state than the kind of fine-grained state, nonetheless, I think, I mean, this is a tentative answer, so I'll be interested to know whether you think it's correct. But I think that perhaps we could still say that quantum mechanics is the source of the probabilities in a kind of analogy to the method of arbitrary functions or objectified credence view. So in that case, the initial source of the probability is credence, but then the values of the probabilities are determined by the dynamics. So likewise in stat mech, we could think that the source of the probabilities is the quantum state, but the values of those probabilities are determined by the dynamics, which together with the initial quantum state determines the choice of coarse-graining. Okay. So should we think of these, I said there's these two different routes where we can think of stat mech probabilities as being quantum probabilities, the global and the local. Should we think of these as being kind of competing, or can we think of them as being kind of complementary, like they kind of boost each other to think that this is really the way to think about probability in stat mech? So the key difference between them is that the second path, the subsystem path, leaves it open whether the quantum state of the universe is mixed or pure. If the universe is in a pure state, then the entropy is zero. But the reason you might think there's some kind of tension between the two paths is that on the second path, if the universe is in a pure state, then the entropy is zero. Whereas on the Mentaculus, the entropy of the universe is increasing. And I think there's sort of a peacemaking move, which is this. So perhaps we can say that it's the Gibbs von Neumann entropy that's zero when the universe is in a pure state, whereas it is the Boltzmann entropy that's increasing in the Mentaculus. So if we think of these as kind of complementary definitions of entropy, we don't have to like pick one as like the one true entropy. They're just definitions which are useful in different contexts. Maybe there isn't a conflict. I think maybe the key question for seeing whether they're getting at the same thing or not is going to depend on the role that entanglement plays in thermalization in the Mentaculus. Okay, so just to wrap up, I've said that which account of row realism you might want to go for might depend firstly on which interpretation of quantum mechanics you kind of lean towards, and it also might depend on what kind of grade of realism you're after. I've said that row realism can be helpful for understanding probability in stat mech. Committing to the state of the universe being mixed allows Eddie to reduce stat mech probabilities to quantum probabilities in a kind of Mentaculus style framework. But even if you believe even if you believe the universe to be in a pure state, you can still reduce the stat mech probabilities to quantum probabilities by thinking about the entanglement of subsystems. But there remains open questions in this more local strategy. But to end on a happy note, I think that even in the weakest version of realism, in the kind of the row realism version, where you're just saying that row tells you something about the world rather than your knowledge of it, we can make progress with rehabilitating the Gibbs entropy. So thank you very much.